So, we've been doing stoichiometry now, so you can figure out how many grams or how many moles of something is going to be produced from how many grams or how many moles of something else. In all of these, what we're assuming is that everything goes perfectly. We're assuming ideal conditions. We do this a lot in science. If we're assuming ideal conditions, that means we're assuming that every single molecule or atom or ion that's able to react does react, will react, that everything is perfect. You know, the temperature is right. There's enough energy in the system. So very often in the real world, as we find the older we get, things don't work exactly the way they're supposed to. And we do have situations where reactions don't run fully, and that's how we would express it. Ideal stoichiometric conditions are not met. So real world conditions mean you can have leftover reactants that you didn't mean to. Okay? When we do stoichiometry, though, we assume ideal. So if you go on to take quantitative analysis at the college level, you will do intensive stoichiometric calculations. It's basically a semester of nothing but stoichiometry. And you are assuming that you're going to produce, if you say you can produce 512.75 grams of iron 3 nitrate, your goal is to get 512.73 grams of iron nitrate. You don't always. So your goal in a class like that is to make sure that you sort of baby the reaction along, make sure it's got enough heat, enough energy, that you've measured everything perfectly, so you get as much of the possible ideal yield as is able. Okay, so we know everything doesn't always work out the way it's supposed to. We're not living in an ideal world. But with that in mind, we're going to talk about limiting reactants. Okay? So conceptually, when you did your chapter close reading, and actually I think most of you, from looking at your what do you know, a lot of you said, well, you know, why does a reaction stop? Because there aren't enough chemicals left to keep going? Yeah, that's exactly it. So a limiting reactant is the thing that runs out. A limiting reactant is the reactant or reagent that you use up. And once you've used it up, you can't do any more of the reaction. So we have a limiting reagent or reactant. And then, if there's something left over of the other one, you know what we call that? We call it the excess. So we have the limiting reactant and the excess reactant. Okay, so the excess reactant is the thing that you don't run out of. This is the thing that you actually have too much of. So there's left over. We're going to do some practice with this, and then, oh my gosh, next week's OGTs, right? Yeah. So we're probably going to end up doing the soap lab the day we come back from OGT week, because there's no way we can do it during OGT week based on, it'll depend on what the schedule is. So, has anybody here ever made soap? Okay, you're all going to get to make soap. So soap is real easy. We take sodium hydroxide, NaOH, and we take fat. And we can use any fat. We can use olive oil, we can use lard, we can use Crisco, we can use soybean oil, we can use coconut oil, we can use any fat. If you've watched Fight Club, you get the joke. How many of you get the joke immediately? Okay, one. How many of you have seen Fight Club? And some kind of fat. And what you get out of that is soap, which is actually a chemical. Soap is actually a chemical. And you get little bits of glycerin, which I can't spell to save my life.
G-L-Y.
Yeah, I got it. Thanks. You get little bits of glycerin, and I think there may be one or two other products. Pretty simple reaction. Now, soap is good. You can put soap on your skin, right? You've all put soap on your skin, yes. Glycerin is sort of another kind of fat. It's used in a lot of moisturizers and hand creams. A lot of them have a glycerin component to them. Fat. Can you put Crisco on your face? Can you put olive oil on your face? Can you put coconut oil on your face? Yeah. Will it hurt you? No. Nah, it's a good moisturizer. Actually, little old Italian and Greek ladies, especially the little old Greek ladies, rub olive oil on their faces every day, you know. And they have this like fruity, peppery olive oil smell. I love little old Italian ladies. Anyway, sodium hydroxide. Have we used that before?
Pretty sure.
We have. Also known as lye. Do you know what sodium hydroxide? You know how you used to be able to buy sodium hydroxide? At the hardware store. It's drain cleaner. So you dump a bunch of sodium hydroxide down your drain, and it is caustic, which means it will burn through stuff. So the big glob of fat and hair and, you know, last week's pork chop bone and whatever else got stuck down the kitchen drain, that lye just burns right through it. How many of you would like to put lye on your face? That's what I thought. Lye is not something that you want to apply to the skin. As a matter of fact, when we do labs that involve sodium hydroxide, which we did, the copper lab, one of your reagents was sodium hydroxide. I made sure, I told you, be sure you're gloved, be sure you're aproned. You don't want to get sodium hydroxide on you. It burns. Take it from me. I can confirm this through personal experience, having received more than one lye burn in my life. So, when you're making soap, which we're going to do in a week and a half, if you had to choose one thing to be your limiting reagent, the thing that runs out, that when you're all done with the reaction, there's no more of this thing left, would you like to choose the sodium hydroxide or the fat?
Sodium hydroxide.
I think I'd like to choose the sodium hydroxide too. When you're all done with the reaction and there is some of your excess left, you want it to be fat. And a soap that's got a little bit of extra fat in it is actually a good moisturizing soap. Now, I'm going to tell you this. This is my personal story. My dear sweet little sainted grandmother who has, you know, long since gone to the farm someplace else. When I was a kid, Grandma always made soap. She'd get all excited when she got a big batch of lard available to her, somebody butchered or we butchered or whatever. And, you know, Grandma had 40 pounds of lard. Woohoo! Going to make soap. And Grandma would just go to the hardware store and she'd buy a can of Red Devil lye. And we always did this outside. There wasn't a whole lot of protective equipment. There was no source of exterior ventilation. That's why we picked a nice day and we did it outside. And my grandma graduated from high school. She was the first in her family to do that. She certainly never took chemistry. She certainly would not have known what stoichiometry was. And if I had said stoichiometry, in fact, she might have thought that I was cursing in some language that she was unfamiliar with. She was an awesome little old farm lady, but her sphere of experience was fairly narrow. And yet, Grandma made soap her whole life. Now, she didn't do any fancy stoichiometric calculations. She would sort of go, yeah, this looks like about enough.
One day.
Do you think that all of her batches of soap came out uniformly perfect? No, and every now and then Grandma would get a batch that she referred to as a bit strong. That had some excess, what? Sodium hydroxide. Oh, it didn't all react off. And those she would typically keep down by the washer, and she would actually use them on Grandpa's work clothes, which wore out remarkably fast. Well, it did get the stains out. She would just rub it on the work clothes. But anyway, that's what she did. And then she'd have some that she would say, oh, that was an especially fine batch, very, very soft. And those would go up to the bathroom for face washing. Guess what those had a little bit extra of? A little bit of extra fat. Those tended to be the batches where fat was in abundance. And so when you had your finished bar of soap, there was a nice fat residue, and those are very moisturizing soaps. So when you buy soap, and I know a lot of people don't actually buy bar soap anymore. We're into this whole era of body washes and weird stuff like that.
I refuse to use body wash.
Yeah, I think it's ridiculous too. But if you have a bar soap that is labeled moisturizing, guess what it's got as an excess ingredient? It's got extra fat. So as you wash, you've got a little bit of extra fat to apply to your skin, because remember, you're all fatty water bags.
Yay.
You are all made up of little bags of water, and what makes up the outside of those bags are phospholipid chains. Those are fats with a phosphorus on the end of it. So that's all you are, is little tiny bags upon little tiny bags of water contained in fat. So your skin is very happy to have that little extra fat on your face so you don't get too dry. So, how do we figure out? So conceptually, you understand. Let's do a little example here. If I have A plus BC and I want to make AB plus C. You can all see that? Okay. If I run out of A before I run out of BC, A is the what?
Limiting reaction.
It's the limiting reagent or reactant, either one. So this is the limiting. And then I'm going to have some of this left over, so that makes BC the excess reactant. Okay. So conceptually, this is really pretty easy, right? Good. Let's do this mathematically, because that's where the rubber. Okay, so we have a reaction running. We're forming lithium nitrate and iron 3 hydroxide, and we're told that we get 275 grams of each of them. What we want to know is which one of these is the limiting. How do we start this process? It's all stoichiometry, but now what we're doing is we're comparing our reactants. Okay? So we're going to actually do 2 factor labels for one product. We're going to do, no, mass to mass. Mass to mass. So we're going to start off, you can pick either one of your reactants. I'm going to pick the lithium hydroxide because it's there. It's the first thing I see. So I'm going to start off a factor label with my given being 275 grams lithium hydroxide. I'm going to do a factor label that compares the amount of lithium hydroxide I'm reacting to the amount of iron 3 nitrate that it could react. So I'm going to go ahead and set up my factor label for a mass to mass going to iron 3 nitrate. Okay, so we start off with our mass of lithium hydroxide. We're going to convert over to moles of lithium hydroxide. That's this step. We're then going to go through our mole ratio of lithium hydroxide to iron 3 nitrate, and then we're going to convert into mass or grams of iron 3 nitrate. Let's figure up our molar masses real quick. Okay, we've got our molar masses figured out, so we have 23.95 grams of lithium hydroxide in 1 mole of lithium hydroxide, and 241.88 grams of iron 3 nitrate in 1 mole of iron nitrate. The only thing that remains is our mole ratio. So for every 3 moles of lithium hydroxide that react, we can react 1 mole of iron 3 nitrate. Now let's do our math. Okay, so what do we get as an answer? 925.77, etc. Yeah, with sig figs it'd be 926. And that's grams of iron 3 nitrate. What does that mean? So you can all get a number at this point. Getting a number, did you find that stoichiometry is pretty easy? It's lovely. You plug things in, it's formulaic, you get a number. Awesome. But what does the number mean in this case? Oh. Well, I'm going to give you a surefire way to never, ever, ever screw up limiting and excess reagents. Okay? It's a sentence that I actually insist you write until you prove to me that you can do these off the top of your head, because frankly, I still screw this up, and I've been doing chemistry longer than you've been alive. So I'm going to put the sentence on here. Okay, blank grams of blank could react blank grams of blank, but we have blank grams of blank. Therefore, we, A, run out of blank, or B, have blank left over. Doesn't make a whole lot of sense, does it?
Yes, it does.
It's going to in a second. So what goes in your very first two spaces are your given. Whatever you started this factor label with. So 275 grams of lithium hydroxide. So the first two blanks are filled in from your first two spaces of your periodic table. Number 2 is from the answer to your factor label. Could react, and we're going to go with our sig fig number, 926 grams of iron 3 nitrate. Number 3 comes back to your original givens. So you have to go back to the text where it said, we are giving you this many grams of this. How many grams of iron 3 nitrate were we given? 275. But we have 275 grams of iron 3 nitrate. Therefore, are we going to run out or are we going to have leftover? It's okay. I do this because until I write this sentence, I often go, we're going to run out. We're going to run out. So, the word that I didn't put in here because it doesn't work in both situations is only. 275 grams of lithium hydroxide could react 926 grams of iron 3 nitrate. But we only have 275 grams of iron 3 nitrate. Therefore, we run out. We run out. So, which one of these is the limiting reagent? The iron 3 nitrate is your limiting reagent in this case. So we've now answered this question. We know that the 275 grams of FeNO3 3 times is the limiting reactant. Well, now we want to know how much of our other reactant is going to get used, because we know now that the excess must be the lithium hydroxide.
That's not good.
No, that's, I mean, in this reaction we don't care. We're not making soap. We're not putting this on our faces. So, how much remains? Well, we can figure this out doing the exact same thing that we just did, but backwards. So now we know that we're going to use up all 275 grams of lithium, or iron 3 nitrate. We're going to start a factor label with that. Okay, so we're going to set up the same kind of factor label we did, but now we're starting with our limiting reactant, because we know that all of our limiting reactant is going to get used up. So, 275 grams of iron 3 nitrate, we'll convert that into moles. We've already got, and then we go with our mole ratio. So for every 1 mole of iron 3 nitrate that we react, we can react 3 moles of lithium hydroxide. Molar mass of lithium hydroxide is our last step. 23.95 grams of lithium hydroxide equals 1 mole of lithium hydroxide. Now we're going to do our math. Okay, anybody else got 22.2786, etc. grams of lithium hydroxide? Okay, so we've got a number 81.688, etc. With sig figs, it'd be 81.7 grams of lithium hydroxide. What does this mean? So we're going to go back and we're going to do the exact same sentence that we did before. Okay, so we've got our sentence, and in this case we know that lithium hydroxide is the excess reagent, so I went ahead and said, so we have blank left over. Same as it was before. Number 1 is that given here. So 275 grams of iron 3 nitrate could react, and same as it was on the last one, Gesundheit. Number 2 is the answer to our factor label. And we're going to sig fig this, 81.7 grams of lithium hydroxide. But we have, and number 3 goes back to what we were given originally. How many grams of lithium hydroxide were we told we had?
75.
275 grams of lithium hydroxide. So we have blank left over. How do we figure that out? This number is what you were given, the 275, minus the 81.68 blah, blah, blah. So we get 193 grams of lithium hydroxide left over, which is ridiculous. Somebody didn't do a good job of setting up their calculations before they decided to give you 275 grams of each. That's just silly. Do these seem fairly straightforward? Okay. We're going to do a lot of practice with these tomorrow. That's all we're going to do tomorrow is practice with these. I can assign you some of the problems from the book so you can go home and look at them if you're so inclined. You know what? I'll just hand you a practice sheet when you walk in tomorrow. How's that? Okay. That's it. Practice tomorrow, FIP on Thursday.